Let us suppose these bodies are moving in a plane without friction or gravity. Such a motion has this interesting property. This line with equally spaced points and this point give a series of triangles of equal areas, equal bases, same altitude. No matter where the point is placed, still the triangles are of equal area. Which leads us to the topic of this film. Had this body not been struck by the blow, this would have been its path. Had it been struck by the blow while at rest, this would have been its path. In one of our measures of time, the body traveled the diagonal of a parallelogram. This side is its path with no blow, this side its path if the blow occurred with the body at rest. Isaac Newton used this parallelogram to predict how a body will move when blows act on it. This is how Newton did it. Here are successive positions with no blow acting. Now, if the body had been at rest here, the blow acting toward this point would move the body this far in our fixed time interval. However, if it had been moving when it was struck, we construct Newton's parallelogram and so find that it will arrive at this position in the given time. This triangle is the area swept out in 1 unit of time on the new path. And this triangle is the area that would have been swept out had the body continued on its original path. The areas of these two triangles are equal, same base, same altitude. That these two triangles will have equal areas, we've already seen. Therefore, these two triangles are equal in spite of the blow. Equal areas are swept out in equal times. Let's carry this farther. Suppose another blow is directed toward the same point. Again, the body is deflected. We find two more triangles of equal area, and both are equal to the previous one. Thus, Newton proved that for a series of equally timed blows, all directed toward one point, equal areas are swept out. There will be a similar path with more straight segments if there are a greater number of blows with less intensity. Suppose we have even greater frequency of blows with less intensity. Our figure is becoming a smooth curve. Equal areas are still traced out in equal time for any given time interval. Johann Kepler observed that in the orbits of planets, equal areas are swept out in equal times. Newton proved Kepler's second law by showing that this centrally directed force is the sun's gravity, and thus planetary motion conforms to the law of equal areas. Newton's proof goes further. He showed that if forces applied to this moving body are directed either toward or away from a given point, equal times of travel still correspond to equal areas swept out. And again, as our blows are more frequent and less intense, the path becomes a continuously curved line. Even here, when equal time intervals are marked along this path, equal areas are described. With forces of any magnitude, directed toward or away from a given point, a body obeying Newton's laws of motion sweeps out equal areas in equal time.